Nope, not that one, this one. So as I mentioned the last time, our topic today is query optimization. And it will bring together a lot of things we talked about, and I will go slowly. So one of the first things that you will encounter is when you write a query, it will actually have to be parsed and verified, right? So you basically get a query. It will be parsed and verified. So what that means is that, for example, the database will check that, if you are selecting on an attribute A of relation R, that relation R has attribute A, its data type is valid, that if you're selecting it's equal to 5, it's actually an integer, so you can, in fact, do a selection, things of that sort. So, so this parsing and verification is just basically compilation, right? So whatever you're learning in programming languages is what happens, right? You've seen compilers and so on to some degree, yeah? So that's really the syntactic part. The syntactic part is fairly easy because it just involves looking at a grammar to see what kind of queries are allowed and looking at the data definition, data dictionaries to figure out what kind of attributes and conditions over those are allowed. So that is great. But then you get into a whole set of semantic issues. So then you basically are going to look at semantic operations, which is where years and years of database research has gone into, so that you can write still things in many different ways, but they will all hopefully be translated into reasonable queries. But it doesn't prevent you from actually writing reasonable queries in the first place. So the kinds of things that you will do, for example, is to look at Boolean logic and look at conditions to see whether those conditions actually are, can be simplified. So for example, suppose you wrote where r.a is greater than 5 and r.a is less than 4, right? So if you were to find this, and then you wrote, or r.b is equal to 10, right? I am familiar with things like this because I teach CS1. So what do we see about this query? So can a value be greater than 5 and less than 4 at the same time? So this part can never be true, right? So this is always false. Since this is false or this, I can actually simplify this to simply say where r.b is equal to 10. Okay? So I don't need to even execute the other one. If I didn't have r.b equal 10, I don't even have to execute this query. I can return you an empty table, right? Because I know nothing will actually be returned. Or if you had, for example, select star from R, where r.a is greater than or equal to 5, or r.a is less than or equal to 4. What did we learn here? It will return everything because, again, this query has a condition that's always true, right? Regardless of which value of r.a it is, it will either satisfy this or this. So this is actually always true. So instead, I would like to do select star from R. These are obviously the simple stuff you can do, but there's much more complicated logic processing to simplify your Boolean expressions. Get rid of Boolean expressions that cannot be true. One of the things you will see is that as we actually see statistics being kept, that you will also know, for example, if there's even a value that is 4 in the database or not. But that'll come later. So this is step 1, but you can do a lot more. One of the things that you will end up doing is you will rewrite queries. And you will rewrite queries to eliminate certain problems. So you will try to get rid of nested queries. Queries, if possible. And I would try to rewrite nested queries to be uncorrelated. Make nested queries if possible. Whenever you have a view in the from, so if you have regular or anonymous views in from, translated to joins when possible. This is not always the case that it is possible, but as long as possible, you try to simplify your query to make them simple joins, simple operations, select from where, and get rid of as many nestings as possible. So, for example, I told you explicitly many, many times, if you have something that says attribute in, select from where, you will most likely able to write the same thing without nesting, right? So ultimately what I care is that you learn not to do this, not leave it to the optimizer, but the optimizer will also try to help you, because there are sometimes you cannot avoid that, because you are writing your application using views that are defined, for the programmers, and then those views have to be translated. But to the degree it's possible, you don't want to use nesting. So if you do have nesting, think about the nested part. So if you were to have a query like this, select from where, and a not in, another select from where, like this. Okay. So in this case, you can imagine that this query will be optimized separately. And this query optimized separately. And to the outer query, this query here, let's call this QA. QA is basically a subroutine. Like for every single tuple, execute this subroutine. But outside of that, I'm not going to talk about how you optimize nested expressions. But one thing that I will tell you is that most often, if you avoided them, you would get faster queries. Not always. If you have a not in, you can look and see if you can write it using except, right? Sometimes possible. Sometimes possible to do it with group by and count. As much as possible, it's better to avoid nested queries. So, but it is not as simple as you would think, okay? So let's look at this one first. Okay. So you have the query up. It says r.a, r.b, from r.a is in, select s.a from s. And then here, I've written the same query like this. So the question that I have for you is this query identical to the above query? Okay. So the thing that I want you to remember that these actually can be tricky. It's not like straightforward that you can always take a query and rewrite it as such. You have to really care about a lot of other details. So are these two the same? Are they going to return the same results? Okay. Shine that SQL knowledge that I've given you, or that you already had. Okay, let's get a vote. Are they, how many of you say they are always the same? How many of you say they are sometimes different? Okay, you're making progress. How many of you can tell me one reason that they could be different? Yes?
Because the second query, it loads in the front end loads S once, so you get the idea from S once, but in the first query you're loading S every single time you do a comparison.
But that is just the cost, right? And how about the results?
Yeah. So in the meantime, during the time that we do it, where on the SIA from S, the data in S can be changed from another query.
No, but that's true. But that's like the least of my worries. Oh, okay, that is true. But if I were to lock it so it doesn't change, that's not the problem. Yes.
I think the amount of duplicates could be different. So unless it is like the state for both of them, the result might not be the same.
So like if you have multiple SA values here, you will get one article for each one, right? Okay, so this might return duplicates, this might not. Okay, what else?
Null values won't return in the first one, but they will in the second one. If you have a date that's equal to null, it'll return.
I think it's the reverse, but I think you are right. So if, no, I think it's true both cases, if you're on the right track. Okay, so let's follow that. So if R dot A is null, right? So so null will never be in a value, even if this contains null, right? And null will never satisfy the 0, right? So R dot A, what you have to say is null, right? So they are both true, but you're on the right track, right? So if there is no value here, right, you are going to return the R. If this relation is empty, let's put it that way, right? If this relation is empty, you will return nothing here, you will return nothing here. Oh yeah, okay. I think that what I was thinking is not true, so far we only have the duplicate values. But this would be the same kind of problem if you had not in here. Then this would return anything even if this was empty, whereas here, S has to have something for you to return something. But yeah, all right. Well, I failed. But these two are not the same because of the distance. Okay? So that's the winner one. And if you were to put distinct here, they are not guaranteed to be the same if this can have multiple R and A values, right? So they cannot return the same value, right? Because here you will return one tuple for each R. If you put a distinct, you will return not necessarily one tuple for each R. So you may remove that. So I'm trying to convince you that it is not always super easy to tell that they're identical, unless you know something about the schema. Okay, so let's try this one. Okay, are these two the same? Here, you return a department if the number of machines for that department is greater than or equal to the number of employees in that department, right? Here, you return the department if for that department, the department number of machines is greater than or equal to the number of employees. Are they the same? This one I stared for a while and I was writing it. The person who wrote this one was smarter than me. So when you're looking at these, ask yourself a few things, right? So this count, can it be 0? Can this count ever be 0? Nope. Not in this one. For this to ever return 0, what do I need? I need the left join, right? So the count is always because these values cannot be null unless I did a left join, right? Whereas this one can actually be 0, right? So this count can actually be 0. There could be no employees in one. In fact, if there are no employees in a department here, right, you will still return that department, whereas here you will not return that department, right? And in fact, if an employee, no, that's so basically, when you're rewriting queries, it is not straightforward. It is complex understanding of the semantics of these queries, as well as your schema is needed to be able to do this. And they are not necessarily the same, so the database has to do a lot of guessing, and sometimes it cannot rewrite. So because of that, it's important that you know how to rewrite these queries so that you can figure out the better different versions, and you can try which ones are more efficient, and we will see how you can do that. Okay? So once I have taken my query and hopefully have rewritten it to remove all of these problems that may slow it down, what I would like to do is convert it to a query tree. So a query tree is a very simple concept. You basically take a query, something like, for example, select from R and S, where R dot A is equal to S dot B, and R dot C is equal to 10, and R dot D is greater than 5, or let's say S dot D is greater than 5, and then I want to return R dot C and S dot E. So what I would like to do is I would like to represent this as a relational algebra operator. So you can do this in many different ways. One of the main things that we learn about relational algebra is that there are many different ways to represent this. So here's one possible way. So I have relation R and S. In a query tree, your relations are always the leaf nodes. And from this, I'm going to select R dot C is equal to 10. Then I'm going to join on R dot A is equal S dot B. Then I'm going to select on S dot D is greater than 5. Then I'm going to project on R dot C and S dot E. So my objective is to generally create a query tree of anyone, then find ways to change this query tree without changing its meaning. Take the expression, convert it to a query tree, but then look at what types of things are possible for changing this query tree. So basically, there are some very simple, straightforward rules that you can apply for query tree rewriting. So these are called algebraic equivalences. And some of them are very straightforward, but let's write them down slowly. Okay. So for example, R join S is the same as S join R. Does that make sense? There is no difference. It's a symmetric operation, right? Yeah, that's right. Thank you. Thank you for not sleeping. So you can shuffle it in any way, as long as the attributes are named unambiguously, right? I was like so anal about that in the beginning of semester. You can write it in any way you want. You can also write it in any way you can basically put parentheses anywhere you want. It's associative, right? So you can say R join S join T like this is the same as, so first joining R with S, then joining that with T will produce the same result as joining S with T first and then joining that with R. So if you combine this with the above, that means I can take a join and I can randomly shuffle any possible combination, right? Assuming that attributes are renamed so that, conditions are unambiguous. This will always return the same result, okay? And if there are conditions, the same conditions continue to apply, right? So if you have condition 1, condition 2, let's say join condition 1, so you will continue to use the same conditions. It's not just for equality, it's just for any join condition. You can do them in any order you wish. So join can be shuffled. The second one is projections. So this is joins can be shuffled. You can add projections any place as long as they don't change the logic, right? So for example, you can add a projection at any place as long as it doesn't remove an attribute you need later on. So for example, if I had, what was the query that I had? I had project on r.c and s.e from join of r and s on r.a, s.b. Okay. So if I needed to do this, what I can do is I can add additional projections. So before I join, I can project from R only the tuples that I will need after that point on. So let's say I'm going to project some stuff from R, then I'm going to do a join, then I'm going to project some stuff from S, then after the join, I'm going to add these two. So that means as you read tuples in R, remove all the attributes except for attributes you will need. So I do need r.c because I'm going to ask that later. And I also need r.a because that's needed for the join, right? So I can add r.a and r.c. And the same thing for this one. I can add s.b and s.e. Now, why would I do this? This seems completely cosmetic, right? I mean, like if you were to write this in like when we are first learning relational algebra, I say this is good for you mentally, but it does nothing to the correctness, right? The thing that it does, however, is there's a very significant saving because as you read tuples in S, I don't really need to keep all the tuples, all the attributes. Because remember, I'm reading the tuples into disk pages, memory blocks, and they take up some space. But if I have fewer attributes to keep, I can probably keep more tuples. If I'm going to remove duplicates, but I only care about two attributes, then I only need those two, so I can put more stuff in, so I will need less memory, right? So this is going to result in a lot of savings. So overall, you can assume from now on that you will never keep attributes that are not needed above you, upstream, right? So you will basically are always removing attributes as long as you don't need them. You will be removing duplicates if you have a duplicate removal above and doesn't change the results below. So this is one of the most common ones. Now we come to the most common one, which is selections. So selections can be pushed up and down. So if you have a join, you can push selections above or below it. So for example, if I have selection of s dot c equals 10 after R join S, meaning that join R and S first and then select on this, it is the same result, exactly same result as first selecting s dot c equals 10 from S, then doing the join, right? So select first then join, or join first then select. So you can push through a selection further down in the query tree, or if you had this, you can push it up, further up in the tree. Right? So why would I want to do that? Well, there are two different things, right? So let's try to see a simple example and then use that to kind of judge why this is very useful. So for example, let's say that I have all right. So this is the expression that I have. Remember, I can push selections up or down. First, I'm going to push selections up. This is generally what happens. You first push all your selections all the way up. So what I get is R join S, R dot A is equal to S dot B. And I have R dot A is greater than 5 and S dot D is equal to 5. Are we okay so far? I pushed it up, okay. Now I'm going to push the selections down, okay. So now let's push it down. So I have R dot A is equal to S dot B. So I have R dot A is greater than 5. And here I have S dot D is equal to 5. And S dot B is greater than 5. So where did this one come from? Because I'm selecting R dot A is equal to greater than 5. And I'm going to do the join of finding all values of S dot B that's equal to an R dot A, right? So if R dot A is greater than 5, only tuples that satisfy my join conditions will also have S dot B greater than 5. So now I was able to find actually more selections by pushing them first up and then pushing them down. Now, there are two interesting uses that I get from doing this. The first one is that now I have these selection conditions that may be applied to an index. If there's an index that can help me quickly find these tuples, that may be better than actually reading the relation alone. So I don't need to necessarily scan the whole relation. Maybe I can do this quickly. Okay? Depends on what other attributes I need, but it may be very good. So these can open up new indices, right? So this may be potentially good for finding applicable indices, or as we call it, access paths. Okay? Now the other thing that's very useful is that instead of reading all of R, I'm going to read R. As I read the tuple of R, I'm only going to find the tuples that satisfy this, and then only those tuples I'm going to do the join with. So that means the join is actually going to be smaller, so I'm going to produce a smaller join, and probably cheaper to compute because I may need to do fewer passes over this when I'm doing block nested loop join. Remember, in the block nested loop join, you take the outer relation, fit it in some number of blocks, then read all of the inner relation once. So you will read the inner relation as many times it takes to fill the relation from here into the blocks for this join. So I may end up reading this fewer times because this is actually smaller, right? So if you are very sophisticated in your understanding, that can be even better because once I read this and find the tuples that satisfy this, the next time I read S, I don't need to read S again. I can write this to this and then read that smaller relation that can actually even be faster, right? So the whole point of cost in database operations is reducing the number of reads and writes you have to do over the relation, right? So this is what this is really trying to do, is to reduce the relations so that the joins are smaller and are cheaper, right? So the thing that we can say is that pushing selections down used to be so important that almost always your database will push selections all the way down, okay? So old systems had a basic heuristic that said push selections down always. But it turns out that this is not PBS, this is databases art. So it turns out that there are cases where pushing it down may actually hurt you because you maybe could have done some other type of join which you cannot do if you apply an index, right? So new databases decided that instead of using a heuristic, which is, so old class, what we are going to do is we are going to basically include this as a potential way of implementing this query, and then look at different plans and find the ones that is least cost. So instead, what I want to do is look at all options and find the least cost option. Okay? So these databases, which is pretty much any database you use today, employ something we call cost-based optimization. They call this CBO. Now, how does it do cost-based optimization? Well, it does it exactly as we have been doing in class. You're trying to look at what is, if I use a block nested loop join, how many times do I have to read? But this only works for one operation. The point is that since you're going to chain different operations in a query plan, you also need to know what is the expected size of an operation in stream, right? So to be able to really do cost-based optimization, you also have to estimate the result of different queries before you execute them. So you need to actually write an estimator of cardinality of outputs meaning expected number of tuples in a query. And even though you know how many tuples there are, you also need to know how many disk pages that it takes. So size of output, which is number of pages needed. So this part is actually very easy if you are the database because you know what attributes you are keeping and what's the size of those attributes, right? If you're keeping 2 integers, 4 bytes each, you know it's 8 bytes per tuple. If you're keeping, 2 character strings, each one is 10 characters long, you have 20 bytes, right? So This is possible because of what the schema is, telling you. So this is the part that I will save you from. Though in past years, I've actually asked students to estimate that too. But for this lecture, we will keep you away from this. But you can estimate if I have 10,000 tuples that, these tuples have these attributes and this many number of pages needed. Okay? So what we're going to do next is give a break. Then we're going to talk about how you can do estimation. Okay? And we'll start simple and get more sophisticated. And then we're going to take that and build on the next step of optimization of finding the best possible query plan. So let's give a 5-minute break and then go back from here.